Okay, is everything perfect now? Okay, so there are many ways to define information geometry. Everybody it's like when you see an elephant and you recognize an elephant or from a non-elephant, right? So, but it's always delicate to give a very formal and definitive definition of information geometry. From a geometric viewpoint, you can say that maybe it's the geometry of dual structures, and this will be my talk today for the introduction. So. Okay, so basically, the field of information geometry was born by asking oneself what is the geometric structure of statistical models. Like, for example, if you have a space of Gaussian distribution or a space of categorical distribution, what is a nice geometric structure on that space? And people, especially the Russian school, look at what is the definition of what is statistical invariance. And the goal at first was to use the language of geometry, like the notion of what is an information ball, or information projection, a bisector, to design algorithm in statistics and to get more intuition of what statistical algorithms do, and also to use the notation of tensor calculus to look at information loss of higher order. So that was the original motivation. But by doing so, we unravel some very nice interplays between statistical and parameter divergence with the geometric structures. And of course, it has unraveled also many kinds of dualities. Right? We see there's a notion of dual connection, there's a notion of oriented distance, and dual divergences. There's a notion when it is flat of Legendre duality, notion of dual representation, and so forth. So basically, it's a land of duality. And this is why I think maybe information geometry with a very broad scope could be thought as a structure of duality somehow. Okay, and what we do with my colleague Frédéric Barbarescu is we co-organize every 2 years a conference that is called Geometric Science of Information, GSI. And the thing is to connect also information geometry to many different areas of geometry, like for example, geometry of domains and cons, like the work of Kozul and Siegel and Wimberg. Because information geometry has not so much dynamics into it, people have been looking at connection with geometric mechanics, like symplectic and contact geometry, thermodynamics, thermostatistics. So basically, it's a very wide scope of the geometric model that we can use for studying models, right? And we call it GSI, and it has been organized since 2013. And this year we'll be celebrating the 10th anniversary. It will be end of August in Saint-Malo, which is a very nice place in France. It's something like 2 hours by a rapid train from Paris, very easy to access. We have a few keynote speakers, so you can check on the site. And the conference is almost full, but there's still a dozen of places if you are interested to register and attend. Okay. So let me have maybe a short introduction to the main concepts of information geometry in 15-20 minutes. What I want to do is to convey the notion that is crucial, the notion of dual structures. So basically, it's like when you go to the subway and you make your sandwich, you choose ingredients. You can build your own information geometry in very simple steps. First, you choose your manifold, right? So basically, you take a domain, like for example, parameter domain of multivariate distribution, and you view it as a manifold by saying that your domain is a chart, right? So usually you have one single chart in information geometry, a global chart, which makes things easy. Then on this manifold, we have flexibility to choose a metric tensor, a Riemannian metric tensor. And this Riemannian metric tensor will define on tangent spaces here at a point P of the manifold. It will define the length of vectors, of tangent vectors, and it will also be able to define the angle between two tangent vectors, right? So this is a very important notion. But in information geometry, we have also a flexibility to choose another affine connection. What is an affine connection? From the viewpoint of differential geometry, it's also called a covariant derivative. It's one way to differentiate a tensor with another tensor, but basically what it does in practice is that it connects tangent planes that are on different location of the manifold, and it also allows you to define a geodesic. So for example, here, my connection nabla will define this geodesic in red. And here, when I have a geometric tensor, we have a default connection, which is called the Levi-Civita connection, which is in purple, right? So now, if I choose just metric tensor, I have a default affine connection, which is going to be able to connect tangent spaces. But if I choose an affine connection, now I have two ways to make a geodesic, one by the Levi-Civita connection in purple, and one by my affine connection. And basically, in information geometry, we have a dual connection, nabla star, which can be written as 2 times the Levi-Civita connection. And what it does, it does you, so you have chosen your red connection here, and you have a blue connection, right? And when it is Levi-Civita, everything collapses to the purple things. So if you stay with the Riemannian geometric modeling, basically you don't have anything, right? So basically you just choose a manifold tensor affine connection, and you get a dual structure, which is usually written by this quadruple MG nabla star.
Sorry.
Yeah.
Just for this, I mean, I've heard this many times, but so 2 tangent planes at P and Q, and the connection is trying to connect all the points.
No, the connection, basically the connection, the definition is covariant derivative, but with that, you can also define what is parallel transport. Parallel transport is when you have one vector in a tangent plane and you want to transport it along a smooth path to another tangent plane. And this is also defined by connection, right? And geodesics are autoparallel path, and basically it's also defined by connection. So basically a covariant derivative defines you as a differential operator, gives you also nabla geodesics, which is what we are interested in visually, but also other things, right?
You have 2 lines, and those 2 lines are 2 different things in the same.
Yeah, and basically we are going to have this connection during here, so that by taking half of them, we find the metric connection induced by the metric tensor. This is really the concept of information geometry. So once we have a pair of connection like that, so this is my last slide, right? You choose 3 things and you get that. But somehow you got more. You got a 1 parameter family of dual structures once you do that. Because what you can do is you can compute something that is called the cubic tensor or Amari chance of cubic tensor, and from that you can derive over pairs of connection, which are called the alpha connection, plus and minus connection. Yeah? So basically, if you have 1 dual structure, you have a family of dual structures, and these are called the alpha geometry. And when you have the 0 geometry, it is called Riemannian geometry. Right? So now I didn't talk about statistical models, Fisher information, or anything like that. I just presented the very fundamental aspect of it. So of course, it has been done because at first people looked at the parametric model, P, theta, which is in my domain, so it defines a manifold. And what has been done is that people have taken at first by curiosity the Fisher information, okay, as a metric tensor. So if it is a regular model, it is a positive definite matrix, and it defines a metric tensor that is called the Fisher metric. So you have Fisher metric and Fisher matrix information, which are 2 different things, very closely related. And the cubic tensor that I mentioned before can be computed with the log likelihood partial derivative like that. And then you get a family of alpha connections. This is the work in the late 70s, 80s by Professor Amari and Nagaoka, right? So this is very come up with that, right? And of course, when we have alpha equal to 1 and we plug it into here, we have what is called the exponential connection. And when it is -1, we have the mixture connection, which was found by Darwin in the late 70s. So what we are very familiar is that if we take alpha equals to 0, we have Fisher-Rao geometry. So basically, it's Riemannian geometry for the Fisher metric, right? And this is what has been found by econometric statistician Hotelling in 1930 and Rao in 1945. This is as a curiosity at first, right? And then statistical invariance studied by Chemtsov in the 70s, and the dual structures of alpha geometry by Amari and Nagaoka in the 80s. So This is a visualization of the Fisher-Rao manifold. Basically, here you don't take dual connection. Everything is a metric, is a Levi-Civita connection. So they are self-dual, if you prefer. It's a zero geometry. And for this special case, you have a distance that is defined by the Riemannian geodesic length, right? But for alpha geometry in general, you don't have necessarily a distance associated, right? So the special case of Fisher-Rao or the zero geometry, you have also some extra things that comes from the Riemannian structure, which is the distance, the metric distance of Riemannian geometry. But you can also compute this dual structure from a divergence. So a divergence is a smooth distance function, if you like. Of course, we know about the Kullback-Leibler relative entropy divergence, P of LOPQ. And if we take a parametric model, P-theta1, P-theta2, and if we take, let's say, Kullback-Leibler divergence, we get something that is a parameter divergence here, right? Here, I don't have integral. I have, for example, let's say, Brabant divergence here, right? Something that depends on parameter, but not on density, right? So I go from statistical divergence with integral and all that to something that is a function on the manifold, actually on the product manifold, right? On two parameters, theta1 and theta2. And because this is not symmetric, we can define dual divergence here by taking the reverse order, right? And now what Eguchi has done in the 80s is to associate to a divergence, which is called a contrast function in information geometry at the beginning, a connection. And by doing a connection, we have a dual connection then, and we have the metric tensor. And basically what we have is that the dual connection induced by the divergence D is also the connection induced by the dual divergence. So here we have the same star, but it's not the same duality, right? Here is the duality of connection, and here is the duality of the reference, right? So basically this is nice. It's just another way to make this structure.
Here, you didn't assume anything like exponential family.
No. I just want to untangle everything. So because
the definition of the parameter divergence.
Yeah.
Like I know I understand Bregman divergence when you say that.
Yeah.
But other than that, like how
you take any smooth function, you have a manifold, right? Now you take the product manifold. Okay, product manifold, you can take a point is a pair of points, right? And you define a function. So you define a function of a product manifold. This is a parameter divergence, right? If you view it in the coordinate system.
You need some kind of property, right? Like
smoothness. You need smoothness.
Or like identifiability, like every theta1 should correspond.
It should be 0 on the diagonal and some smoothness, basically. Yeah. So actually, the thing that, for example, you give me this, you came up last night dreaming about some dual structure like that. And what we know is that we can realize this dual structure by finding some divergence so that the dual structure induced by the divergence coincides to that. Okay, and this has been done in 1993 by Matsumoto. It says that any statistical manifold has a contrast function, so it means a parameter divergence, right? And also what we know is that if you have this dual structure, you can also realize it by model information geometries. This means that you can find a statistical model so that the alpha geometry of this alpha model will get this dual structure, right? So, and this is more recent result in 2006. Okay.
Wow, so this is basically saying that models can always be used.
Yeah. So this is why I think my last slide of this tutorial will be as a tool for duality, I think. And what I want to say is that now there's a connection between model alpha information geometry and divergence information geometry. And this connection is done by F divergence. Okay. So what is a F divergence? It's a way it generalizes Kullback-Leibler divergence. It is defined, you take a convex generator, okay, Fu, such that f of 1 is 0, f prime of 1 is 1. And you can also enforce a scaling by saying that f prime of 1 is 1. This is what Professor Maris called standard F divergence. And you define the F divergence as this thing, right? And if you have f equals minus log, then you get the Kullback-Leibler, okay? So the reverse F divergence is also F divergence. So this is a reverse F divergence. I put the star here. And it is F divergence for F diamond, where diamond is this thing, okay? So we have yet another duality here, right? This is the third type of duality that I show here. Okay. And of course, if I have a parametric family of models, the F divergence between two members of my model is a contrast function, right? It's a parameter divergence here. And so from that, we can compute the model, the divergence space model, this thing. But because we have also statistical model, we can compute the alpha geometry, the statistical alpha geometry for models, right? And actually, both ways of constructing, they coincide for alpha equals this quantity. So this means that for alpha equals this quantity, you will have this thing, equality. Yeah.
Sorry, I'm still trying to understand. It's quite amazing. So I sub F and then star is on the divergence.
Yeah, so this means that I swap arguments. Okay.
And then, yeah, you go to I of F,
Yeah.
and you swap the argument, theta prime.
Yeah, so this is the definition. Okay, so basically, if you swap arguments, you get this thing.
And this is one dual, I guess.
Yeah, and this
Is
is,
the dual? It's the dual divergence, right?
yeah, it's a dual divergence, right?
But then what is the last one is like you're changing the generating function.
Yeah, so basically, what I can say is that it is a primary divergence for this dual generator. So now we have a dual generator of divergence.
So you can either swap the divergence or you can somehow invert the generating function.
Yeah, yeah, this is a related to perspective function. So this is very well known stuff. Okay. So what I just wanted to tell you at the first is that in this duality based workshop is that information geometry could be a nice tool to look at duality somehow. So I didn't talk about curvature yet, but curvature is a notion not associated to the metric tensor directly. It's a notion related to the connection. But when you have a Riemannian structure, you have a metric tensor G, which induces a Levi-Civita connection, which is a connection, and then you get a curvature from the connection that is induced by a G. Okay. So how can you visualize curvature? For example, if I have here a cylinder and I do the parallel transport from the vector here on the tangent plane here along a small loop, if I come back to the same without position, without angle defect, I have zero curvature. So here we will say that the cylinder is flat. Okay, and if I have some angle defect, once I do a short loop like here, you will see that, then we have some curvature. Okay, and curvature is induced by the connection. So now, why is curvature important? Because in Riemannian geometry, there's something that is called the fundamental theorem of information of Riemannian geometry. It says that there's a unique metric connection that is called the Levi-Civita connection. So there's a canonical way to get a connection. And in information geometry, there's something that I have called very humbly fundamental theorem of information geometry. This is not official calling, but basically, if we have a connection nabla, which is of constant curvature kappa, then the dual connection is also the same curvature. So if you are basically if you start with a flat connection, your dual connection will be flat. And this is what people say dually flat space. It comes from that, right? And basically, dually flat space for machine learners is Bregman manifold. It's a manifold with a Bregman divergence. I will tell you why after. And what is good is that how can we recognize that the connection is flat? Is that if to define a connection here, you need to define, let's say in dimension D, D cube function by the so-called Christoffel symbol here, gamma. And if you find a coordinate system theta such that whose coefficients are zero, then you know that the connection is flat. So basically. And if the connection is flat, then basically the differential equation to characterize geodesic become very simple because this term disappears. And this means that in the theta coordinate, your geodesic are just line segments. So basically you can compute many things like intersection or everything is very precise because basically the geodesics are just straight line segments in the parameterization. So there's something that is very powerful is that if I take a dual structure here, and if I know that it is dually flat space, so this means that nabla is zero, curvature of nabla is zero, then I know that I can realize it by a divergence. I told you that before, right? But I know that also the canonical divergence that realizes that is the Bregman divergence. Okay, so what is the Bregman divergence? I guess we all know, and I will call this definition here as this vertical gap. I think this is very familiar for the audience here. And so basically, this is why I said you can call, let me see. This is why I said that you can say that a dually flat space can be called a Bregman manifold if it rings you a bell better. And of course,
So this was, you said this before for in general, and what is the special case here?
it's dually flat.
Oh, specifically.
Actually, yeah, and actually we have one other extra recent result that if it is of constant sectional curvature, there's a canonical divergence that is called the logarithmic divergence by which extends also this Bregman divergence. So
Is this like one, like both ways? Like,
no, I will show. Basically, you can find F is not unique. I will show you, but basically, geometrically, it means that it is the same geometry. I will give example. I just wanted to have the purest definition of information geometry to tell you about the duality. And because we have a Bregman divergence for a generator F, we have also the convex conjugate, okay? Which I show here. How can you understand the convex conjugation is that if you have a convex function here, you plot the epigraph, okay? So you have this domain here. And if you're familiar with polytope, for example, we can represent a convex body as a convexel of the points on this boundary, or as the intersection of the supporting half spaces, right? And basically, this gives you two coordinate system, theta and eta, okay? And what we have is that we have, if it is a lower semi-continuous convex, then we have Fenshaw-Morrow biconjugation theorem, which means that the duality is involutive, so F star star is F, okay? So in that case, what I have is I can define a very nice kind of function, which are called Legendre type function. And the convex conjugate of F is defined by this Legendre function. And we have this Fenshaw-Young inequality here. And in that case, we have the gradient of with Legendre type convex function, which are inverse gradient of each other. Okay, so this means that we can define an equivalent to the Bregman divergence. Bregman divergence is defined with both theta parameter as a mixed parameterization between one coordinate system and the other coordinate system, and it's called the Fenshaw-Young divergence here. Okay. Okay, so basically the Bregman divergence, you can also write it equivalently by taking the dual convex function and the dual parameterization. Okay. And one important thing in Bregman manifold is that we have a generalization of the Pythagoras theorem. This means that if one geodesic here is Fisher orthogonal or metric orthogonal G to the dual one here, okay, then we have this 3-point equality here. So this point here can slide. This is let's say this is a primal geodesic. I can slide this point here. I can slide this point on the dual geodesic. I will always have this 3-point property. And this 3-point property is equivalent to that. Okay, so this is just an extension of Pythagoras theorem, and this is just an extension of the law of cosines in Euclidean geometry.
Sorry, I've been trying to understand this for years. So now that you're here,
yeah,
I'd like to understand. So,
actually, I can confuse you more with this slide, and then I answer your question, right?
okay.
Okay, I confuse. So the thing is that because in the previous slide, what I said is that you can move this point here, right? On the primal geodesic and dual geodesic, for any position here, you will have the Pythagoras theorem, right? Because they are orthogonal with respect to the tensor. Okay.
So is that connected to this red box as well? I am.
So basically, if you expand the Bregman divergence for that, the condition to be
that's what we like.
Yeah.
But
Okay.
where is the gamma PQ T of T?
So eta is nabla F, and it's from the gamma star, which is a geodesic, dual geodesic point. So here this is the geometric equation, and here this is the local coordinate, or if you like, the coordinate equation, right? Okay. Okay. So you don't have to suffer much more. I will come to my argument, and then we will switch back to normal machine learning. So this means that if I told you that I can slide the points, it's possible to find position of the point so that I have a simultaneous dual Pythagoras theorem. So compared here, I will have a triple of points, and for example, the red line here with the blue line here is orthogonal here. and the blue line here with the red line here is orthogonal here. So we can have simultaneous dual Pythagorean theorem also. Okay. So because I have a convex function, I have a Bregman divergence, right? So then from the Bregman divergence, I can compute the divergence information geometry, right? This is the thing, right? And basically this amounts to that thing here. Okay. So anytime you have a domain with a convex function, you can build a Bregman manifold or something that has been also studied as a Hessian manifold. Okay. So for example, for the exponential family, this is the usual construction. We take the log normalizer and we have everything. If you are working with the convex cones, like for example in operation research or mathematical programming, you define a characteristic function. It's a convex function, and then you have dually flat geometric structure. If you take a mixture family, like for example, a mixture of two different prescribed Gaussian distribution, you take minus the entropy, it's convex, and then you have this dual structure, right? So basically what I want to say, information geometry is dual structure, and you can how do you obtain the dual structure? You need to find an affine connection, and then you will have for free the dual affine connection. And this connection you can build from a convex function, a divergence, or a statistical model. Okay. So basically, this is my unconventional thing, is that maybe information geometry could be a generic tool to geometrize duality. Okay, and for example, for divergence, this is what I have explained here, and this is what has been called by dual contrast function. For Bregman, divergence and convex conjugates, we have this thing, and people talk about potential function in geometry. And for statistical model, I didn't talk much, but once you have tangent planes, you can represent vectors in the tangent planes. You have a flexibility of choosing the basis to express your vector. And we have also alpha minus alpha representation, or if you want, arithmetic mixture and geometric mixture duality. And this is the dual, what we can call the dual F representation here. Okay.
Can I ask a question?
Yeah.
So I think for the Bregman style thing, all three things I understand.
Yeah.
But going beyond, let's say, I mean, in Bayes, we have like general statistical models, and we have partition function of posterior distribution. Do you think that the same construction will hold, where the partition function will correspond to an exponential family of the kind that I know at least? Or do you think Bregman already covers all of that?
If it's dually flat, it covers all of that. I will come. Yeah. So basically, here what you have is if you have an object F and you have a duality O star, and if for O you can define me a nabla, then I will have nabla star, and basically I will have a geometric structure to express the duality. This is what I wanted to convey in this mini tutorial. Okay, so it will become a bit clearer from now on. Okay, I have this very unorthodox way of. Sorry?
This was not the math, the one before.
Yeah, but math is okay. This was a concept.
Math is coming, or math is over.
Almost over.
Okay.
So I will show you that the dual flat space or the Bregman manifolds can also give us some very intuitive way to generalize a common concept that is called the quasi-arithmetic means. Okay, this is the second part of this talk. So the goal is to generalize a concept that has been called quasi-arithmetic means to multivariate cases, and to show that the dually flat space of information geometry will bring many intuition and properties for this generalization. So what is the F mean or quasi-arithmetic mean? Basically, you take a strictly increasing and differentiable function F. I think the laser is right on. Let's see. Okay. And you have a set of scalar here, and you have a weight. Okay. You take the arithmetic mean of the F representation, and you take F minus 1, and you get this F mean. Okay. And from that, you can, if F is the identity, you get the arithmetic mean. If it is a log, you get the geometric mean, and if it is 1 over X, you get the harmonic mean. Okay. So you get the Pythagoras mean generalization and all that. And you have the good property of means is that a mean is in between the extremum, right? It's between the mean and the max. Okay, so what we want is this is a concept that has been studied in the 1930s by Kolmogorov, Nagumo, Definiti, and so forth. And we want to generalize this concept where X is not a scalar anymore, but let's say a vector or a matrix. Okay. So first, this means I just want to mention that there's an equivalence class of generators, G and A, so that if they are just differ by a scalar affine term, they yield the same mean. Okay.
Can I ask? In
Yeah.
the previous slide, there's no condition on W, or W is.
It is in probability simple X. It's a weight. It's a weight vector.
Oh, it's a convex sum.
Yeah, it's a convex sum.
Okay, then makes sense.
But for arithmetic mean, you can relax, but you don't have the boundary. So because whose function belong to the same equivalent class, I can just say strictly increasing now. Okay, because if I have minus 1, I will get strictly decreasing. I will get something. So this includes also the power means. Okay, if I have a smooth family of generator, so it is smooth because basically for p equals 0, this thing tends to log, which means that you get the geometric mean in that case. And if I take this family of generator and if I take the quasi-arithmetic means, I get the power means, right? The usual power means, Minkowski or other means, right? Okay. So it's extra family of Pythagoras mean. So what we want to do is to generalize this formula to non-scalar. And for doing that, we face two problems. First, we face the notion of what is multivariate increasing. We have to define properly what it means for a function to be increasing when it is multivariate. And then we face another problem that it is f minus 1, which is always defined in scalar case for smooth things, doesn't always globally exist when it is multivariate, right? In global analysis, we have the implicit function theorem that just gives local existence provided the Jacobian thing. Okay. So what I want to show you that during information geometry of convex function, we'll be able to give a nice generalization of that. So what is a nice convex function, multivariate convex function? It's a Legendre type function. So basically the problem is that if we apply to a Laurent semi-continuous function, a convex function, the Legendre transform, it may be that the domain is non-convex, right? And we want to have nice, this was an example that was a counterexample in 1967. So we want to have nice functions so that if we have theta f and we take the Legendre function, we have h f star, which is also of the same type. And the right way to define it is to define the Legendre type function by this condition. I'm not going to read it, but basically, if we have this nice class of Legendre type function, then also the convex conjugate writes with this Legendre function, and we have gradient map Nabla-F, which is globally invertible, right? And it is smooth, okay? And the notion of monotonicity for the scalar function can be extended to comonotone function. So if I will say that G is comonotone, if in some inner product space, I have this inner product which is always positive here, okay? And actually, the gradient function Nabla-F and Nabla-F star are strictly comonotone function. And the way that you can prove it very easily in 2 lines is that you write the symmetrization of the Bregman divergence, you get this thing, okay? And because this is positive, positive, this is positive, and this is the condition for Nabla-F to be comonotone with identity function, right? So basically, symmetrization of Bregman divergence give you a one-line proof of being comonotone here. Okay, and this is a generalization of scalar things. So the definition of a quasi-arithmetic center, basically.
What's the intuition actually? I don't get it. Like, monotone. So you're trying to like somehow define because we need this vector thing.
Yeah.
But I understand the math.
Yeah.
It's very opposite now. I understand the math, but I don't understand the intuition.
The intuition is that how do we define the concept of monotonicity in multivariate cases?
And you're writing the gradient of that, and then writing the gradient of the conjugate, and you're saying that should somehow be greater than 0.
Greater than 0, right? Basically, it has been used a lot in financial industry. Okay.
Monotonicity, and then you have co-monotonicity.
Yeah. Okay. So basically, the multivariate definition of quasi-arithmetic is this thing. So which is also equivalent because we need to take f to be a gradient map of a Legendre type function. You can also write it like that. Okay, and we make the generalization here just by taking that in the 1D case, in the scalar case. So if I take, for example, a matrix harmonic mean, I take this function minus log det. We know that it is strictly convex and positive. We take this inner product space. Okay, so we have on the simply positive definite column. We have the Legendre convex function here, f star and f theta and f star theta, and we have the two quasi-arithmetic mean. And in that case, you see that the formula are the same, just theta or eta that change, right? It's the same. It defines the same mean, but in general, depending on f, you get a dual pair of operators, a dual pair of arithmetic operators. Okay. And you can also show that those quasi-arithmetic averages are used to parameterize the dual points on the dual geodesics. I'm not going to show you, but basically, if I have two pair of points, I have two dual geodesics, Nabla and Nabla, and if I write in the coordinate system of theta or eta, I can write it as quasi-arithmetic averages. Okay, so this is a natural notion. And if I want to compute a centroid, like for example, the left-sided Bregman centroid or the right-sided Bregman centroid, I can write it purely geometric with this canonical divergence here, according to a pair of connections. So this is a geometric problem, and this is the problem in the coordinate system. And basically, in the coordinate system, the barycenter will be expressed as a quasi-arithmetic averages. Okay. And now we go to empty question before, is that from a convex function of Legendre type, I have a dual convex function, and I can build this information geometry, right? But it's not unique. I can choose different kind of f or different kind of theta, and to have the same one. So, but for example, if I use an extra affine term here, so I change my function f by adding some affine term, it will be the same information geometry here, dually flat, and we will have coincidence. They will coincide. The quasi-arithmetic average will coincide. And now, if I change the parameterization of my coordinate system so that I have theta bar, which is a affine transformation, and I have this, basically the gradient, you write it like that. So basically, you will have equivariance of the quasi-arithmetic mean in the coordinate system, but it is the same geometry. It is the same information geometry. So basically, it gives you a very neat understanding of the relationship between quasi-arithmetic averages and dually flat space things. Okay. Maybe, okay. So this is to answer, but basically what we have, usually when you do machine learning, you start with your Bregman divergence and you have the dual Bregman divergence, right? We play with that. We can express it in a mixed coordinate system by taking the functional Young divergence. But what's happening is that we have a pure space here, a dually flat space, where we have a canonical divergence, which is a geometric divergence, right? It's like Euclidean distance. You don't have the Cartesian coordinate system for sure, or maybe polar things, right? Euclidean distance exists as itself, right? And this distance here exists also, and we realize the Bregman divergence. Okay, so what we have, we can show that basically if you start with f and you make some affine Legendre invariance by changing the coordinate system and affine transformation and adding some affine term to the f, you will get the convex conjugate like that, and it will be the same dually flat space that you have, right? And we can show that we have this property which generalizes the matrix scalar case. Okay. Okay. So for example, for Malanobis square distance, so the square Malanobis distance here, I don't take the square root, so it's not a metric because triangle inequality fails. I have the primal potential function where I can put also some affine term here. I have the dual potential function. If I look at the dual quasi-arithmetic averages, I find that this is the same arithmetic operator, but on different coordinate system, right? So, and of course, this quasi-arithmetic means we can also extend to mixture. For example, if we have a set of statistical components, P1, Pn, and we make a blending, not arithmetic blending, we have to renormalize, right? Because if we take, for example, the geometric mixture, the integral of square root of PQ is not equal to 1. So I put this notation here to say that it is MF mixture. For example, if you have the alpha mixture that has been studied by Professor Amari, you can show that this alpha mixture is also a centroid because it minimizes the alpha divergence, right? So we have also this notion of integration of densities by quasi-arithmetic means. What we can also do is to look at the Jensen-Shannon divergence, which is a bounded symmetrization of the Kullback-Leibler divergence here. And here we see that we have the arithmetic mean. And because I have arithmetic mean, I can change it to say geometric mean or other things, and I can interpret it as a midpoint on a geodesic defined by some connection. So I can define this kind of Nabla-Jensen-Shannon divergence, right? So we get a generalization. Okay, I just want to show you that some nice stuff that has been done by Nakamura in 2001 is how to compute the arithmetic harmonic mean, AHM. So basically, you want to compute the arithmetic harmonic mean between A0 and B1. And what you are going to do is to make this kind of Gauss iteration. You take the arithmetic mean of the two quantities, you take the geometric of the two quantities, and you iterate. And what is known is that in the scalar case, you end up in the limit where the both the sequences converge to the same value, and this value is related to the complete elliptic integral. So this was also proved by Gauss a long time ago. But what we can do, for example, if instead of taking the geometric mean, I take the harmonic mean, then I will have also two converging sequences to the same value. Here is the geometric mean. Okay. In that case, this thing you can compute easily, right? So usually you don't do that because you can just compute that. But what we can do now is I can take matrices instead of scalars. Okay. So I can take what is called inductive mean because the mean is computed by iteration. Okay. I can take two SPD, two symmetric positive definite matrices. I take arithmetic mean, it's SPD. I take harmonic mean, it's also SPD, and I reiterate. And in the limit, what you can show is that it converges to something that is a matrix geometric mean, this guy, G, for two things. And this can also be interpreted as a Riemannian center of mass. So basically, the notion of Euclidean centroid on manifold, basically, yeah. And one way to visualize this operation is that first, you take the arithmetic mean, so you take the midpoint of this connection. You take the harmonic mean, it's a midpoint of another connection. So this is the connection for it's a metric connection. And you can visualize this algorithm geometrically with connection. So I don't want to spend too this, but basically it gives you some more powerful concept to abstract and define geometric means and inductively. Okay, how much time do I have? Maybe
25 minutes, but discussion.
Yeah, I think discussion is very important, right? So I just want to mention one, again, the main point will be that information geometry is purely also geometric result in itself. So let's go to the chain of information. So chain of information, it could be called chain of divergence. Basically, you can define it as the maximum of a skew distance, and here you have alpha affinity coefficient, so it's a similarity coefficient between two densities P and Q, okay? And you take minus log of that is Bhattacharya, what is called Bhattacharya distance, and the maximum Bhattacharya distance for a skew exponent is called by definition chain of information, right? And this was defined, I think, in the year 1952. And it has been used also for a neural network to analyze GANs and so forth. So this is what I said. Basically, it's a Bhattacharya skew distance, and you want to take the maximum of that. And this is also related to Rényi divergence because you can write it for the Rényi. It's just a scaling factor here. Okay. So sometimes people say Rényi divergence or Rényi. In literature, there's several ways to call the same thing. And it has been studied at first because people were interested to find the optimum value of alpha, which has some kind of statistical interpretation in Bayesian hypothesis testing, which is called the chain of error exponent. So So let's say that, for example, you have a mixture model here of two normals. Okay, I have two normal distribution, two components, so the blue and the red, and the mixture here. And I sample from the mixture, and now you need to classify the samples. Okay, so I randomly sample here. So I get, for example, one sample here, one sample here, and I have to classify it either as emanating from the first component or the second component. Of course, because the support of the densities coincide, I cannot be sure, right? Maybe I say that this guy is blue, but it was taken from the red things. And so you have some inherent error that is called Bayes error in hypothesis testing. And this probability of error, you can write it as this integral here. And this is a similarity measure. It's called, in computer vision, it's called the histogram intersection similarity, okay? And now we are going to use another trick. Chernoff, what it did is another trick. So first, you can write the minimum as the center point minus half of the length of the interval, right? You take the mean, the A, B, you take the midpoint, and you subtract half of the length of the interval, and you get the mean. And for the max, you take, actually here it should be minus, right? Yeah, sorry. And here you get the max, and if you take minus here, you get the mean, right? The typo. And basically, you can rewrite the Bayes error as something that depends on something that is called total variation, right? So there's a link between probability of error and total variation. And now, why is Chernoff information useful? Is that because I want to bound this probability of error, and what I can do is I can say, okay, because I can take any weighted mean, because the mean should be in between mean and max. This is larger than PE, okay? And what I'm going to do is I'm going to slice the integral by choosing the right way to make a mixture. I'm going to have closed form solution for the integral, and I can, for example, if I have exponential family densities, and if I take the geometric mean, I will be able to get the optimization for alpha. And this is why it has been studied at first. Okay. So why is it important? That if I take two densities P and Q, I can make this the geometric mixture, P alpha, Q alpha. Okay, so this is the geometric mixture. And I can build an exponential family, which is a one parameter scalar exponential family. And this family has been called likelihood ratio exponential family because the statistics, sufficient statistic here is if you write it in the exponential family canonical decomposition, you get a log P over Q as a sufficient statistics, right? So you can view this arc as a 1D exponential family. So you have an infinite dimensional space of densities, and you can link any two densities and think of it as a parametric 1D exponential family, which is very useful because now you can use a toolbox of exponential family.
So P and Q are not exponential.
No.
But then it's a 1D exponential family with alpha. It's like, what kind of parameter is it?
It's a scalar.
The canonical.
Yeah, and it should be between 0 and 1. But if it is between 0 and 1, this guy has the same support. Even if P and Q have different support, they take the mean of the support here, right? If you take alpha between 0 and 1. So basically show you. But at the end point, 0 and 1 is not an exponential family, right? Because they can have different support, for example. Okay. So if I take the log normalizer of this exponential family, basically I can, if you write it, you will find that it is minus skew beta Shaya distance. And because you know that the log normalizer is strictly convex, you know that this is strictly concave. So basically, you know that you have uniqueness of Chernoff information of the error exponent. So using some result of exponential family, you can derive some result for Chernoff information, and you prove that it is unique. Okay. And maybe I want to skip this thing. But yeah, in exponential family, you have a concept of regularity and steepness, and there are some details here that I don't want to talk today.
That looks very interesting.
So
it looks beautiful.
So this guy is probably the most surprising. If you take a Gaussian distribution, any truncated exponential family is an exponential family. If you truncate it, okay, you truncate support. But it might not be regular, or it might not be steep. Steep means that somehow you can use the dual Bregman divergence, and regular means open domain, which implies steepness somehow. I don't want to go to the details, but basically, we have one way to generically calculate the Chernoff information. Just by looking at the two densities as a likelihood ratio exponential family. So you start with something that is not an exponential family, you model it as a 1D exponential family, and then you apply the generic toolbox. This is the notion here. We can interpret it. So basically what happens is to find this optimal alpha parameter. You can interpret it geometrically as you have two densities on this